Hello everyone, this is Yan-Shu. My research project is reinforcement learning for continuous control. So control is an important task in our daily life. How to make the controller can adapt to an environment with uncertainty is essential. In ILO, an agent learns in an interactive environment by trial and error using feedback from its own action and experience. Even the agent doesn't know the environment, he can still make a good decision if the states can be observed and the rewards are received. This makes RL have high adaptivity to serve as an excellent tool to solve control problems. Nowadays, RL has been widely used in control tasks such as gaming, robotics, and autonomous car. However, because the agent has to be trained by trial and error methods, how to balance exploration and exploitation is always a challenge in applying IL in control. Besides, the stability of IL is also a concern for the control community. In this final project, I chose an IL method called DDPG. The DDPG combines the advantages of a deep Q network, DQN, and the DPG approach. Although the pure DQN approach can be only used in discrete control, it can stabilize the controller. DQN can stably learn value functions due to two innovations. First, the network is trained off policy with samples from a replay buffer to minimize correlation between samples. Second, the network is trained with a target Q network to give consistent targets during temporal difference backups. Given the stability from DQN, plus the aid of the DPG approach. That's why DDPG can do continuous control well. The DDPG algorithm is based on model-free and off-policy RL techniques. Meanwhile, a deep neural network is used for function approximations. As shown in the figure, DDPG consists of both networks. The created network whose input is action and observation. The output is a value of the state-action pair, which is QSA here. In addition, a neural network is used to approximate the actor network's input is state value, and the output is action value. We use theta to parameterize some function approximators. Modify for actor critic and using soft target updates, rather than directly copying the weights. We create a copy of the actor and the created networks Q and mu respectively to calculate the target values. For the implementation, first of all, a simulated environment must be established to implement the DDPG algorithm. The environment should be built based on physics or rules. Therefore, we can observe the states of agent and let the agent do actions to interact with the environment. Therefore, OpenAI Gene is used to establish the environment. The RL approach can use the action and the states to build the actor network to maximize the rewards without knowing the models utilized to simulate the environment. A pendulum is used to demonstrate the ability of the DDPG algorithm. In the beginning, the pendulum is inverted. There are three state observations, and the action has one variable to be adjusted, so the pendulum can be swung up. During the training, we have to add noise in the action space, so the agent can explore the environment. The extent of the exploration is decreased when absolute increased to around 100. In the meanwhile, when extent of exploration reduced, we can find out the reward value increase with increasing episode. That is the first proof that RL training works. However, only reward values might not be sufficient to guarantee an RL algorithm is effective, because some unexpected behavior might also happen. For example, a bipedal robot traverses pits using only one leg to jump. Even if the rewards are high, the prudent approach to evaluate the RL algorithm is to observe its states and actions as well. As you can see, after training, the control move is around 0 and almost stable value. And for the states, we can see the angle and the angular speed is almost 0. So here are the take-home messages. Another deep RL approach, DDPG, solves the stability issue that most typical RL approach have by combining the advantages of DQN and the DPG approach. And also, a benchmark environment, the pen endurance when up can be effectively controlled by the DDPG method. And DDPG and other deep RL approaches are widely developed and used in control tests, especially in gaming and robotics nowadays. Thank you.